Okay, so this is part 2 of the net force video. This is the more complicated example, and then at the end of the video is kind of like the most AP Physics 1 thing that you need to know. And so this is a situation where we have two vectors that are both at different angles. And so instead of going with north, south, east, and west, I went with the angle away from the x-axis in the positive or negative direction. If I were to look at this visually, right, I would have F1 is 30 degrees above the x-axis, and F2 is 60 degrees below the negative x-axis. So maybe that's like here. Those angles are this one and this one. And so, you know, if I wanted to apply like the tip to tail method of addition, I would have something like this. I would have F1 would look exactly, or as close as I could make it, it would look like this. And then wherever F1 ended, I would try my best to draw F2 off of it. And so the net force on those two is going to be this arrow. Now I drew this by hand, so I actually don't, I mean, I know the answer, but I have no idea if I'm like drawing this at a reasonable angle. It's just my best guess. So unless you have like a scaled drawing, you can't really do net force with a picture. You can get some like mathematical ideas, but you can't really do everything. So the way that we work component method with this one is we do a lot of our trig up front, then we add and subtract, and then we do our trig at the end. So I can find the following things. I can find the x and y components of F1, and I can find the x and y components of F2. And I'm gonna like blow through the trig so you don't have to like sit here and look at it, but feel free to pause as much as you need. So I'm just going to kind of write out all the trig, and we can look at the results afterwards. Okay, so everything is cosine and sine for me, and for these, because the angles are given relative to the x-axis, my x components are cosine and my y components are sine. I'm going to round these to whole numbers, so I'm going to have 17 newtons for F1 in the x direction, 10 for F1 in the y direction, 15 for F2 in the x direction, and 26 for F2 in the y direction. And now I can add my forces. So the net force in the x direction. Here's where I have to be a little clever and do the same thing I did in the simple example. But you know, right and up are positive, down and left are negative. And so for my net force, I'm going to do 17, because F1 is in the positive x direction. And I'm going to do 17 minus 15. Because F2 is in the negative x and negative y direction, 15 newtons is a negative force according to my scheme here. So the net force in the x direction is positive 2 newtons. Next up is the y direction. So net force in the y direction. My up force is going to come from F1, so that's going to be a positive 10. My down force is going to come from F2, and that's a negative 26. So in this case, my net force in the y direction is negative 16 newtons. So I can have a net force that's negative, and what that means to me is it's just pointed in the direction I've defined as negative. And in this case, down and left are those directions. Now I want to draw my triangle. So that's the component method of addition, is this like add the right minus the left, and then the up minus the down, and I have my components of the net force. Now I want to draw a triangle. I always like to draw the x component first, because then it's always the adjacent side is along the x-axis, and that just makes things consistent for me, and I like that. So I'm going to say 2 newtons is in the right direction, so that's the net force in the x direction. And then 16 newtons is directed downward. Now I'm not going to draw this to scale just because I would go to the end of the paper, but this is going to represent the net force in the y direction. So my net force overall is the hypotenuse, and that is the angle. So you know, it ends up being in the same direction as my like tip to tail method. I found it mathematically. I can probably imagine this is not to scale, obviously. This is also not to scale, but it gives me like a better sense of where everything is. So my net force is something I will use Pythagorean theorem for. So net force in the x squared plus net force in the y squared. So just to, I didn't do it in the previous example, just to do this out, net force in the x direction is 2 newtons squared. Net force in the y direction is negative 16 newtons squared. And so my net force, there we go, is, I think it actually just rounds to 16 newtons. Sorry, I guess I did this calculation and didn't think about it. 2 squared plus 16 squared. Yeah, so it rounds. It's not very much larger than 16. So just to make it look different, it rounds to 16.1 newtons. Okay, so that's the net force. Mostly ends up being in the vertical direction. And then the angle, inverse tangent of 16 over 2. And then that angle is going to round to about 83 degrees. So when I put this all together as an answer, I'm going to have my net force is 16.1 newtons at 83 degrees below the positive x-axis. So there is the net force there, and so that's about as, I would say, about as complex as the component method gets if you're making a computation. That you're adding 2 vectors that are both at angles. You have to break them apart into components, add their components separately, and then put them back into a hypotenuse of a right triangle. So we've made it to the end of the video, almost, and we have to talk about Newton's second law, because one of the things that is a huge focus of this course is putting this idea of net force into practice. So here's some notes on Newton's second law. Maybe you pause and write it down and then listen to me talk about it for a minute. But net force is equal to mass times acceleration. So Newton's second law is basically like an object will accelerate if it has a net force that's not 0. And so I'm here to talk about the special case. And the special case is when we have like a Newton's first law situation. If the object is at rest, or if it's moving with constant velocity in any direction, that means its acceleration in a direction is 0, and so the net force is 0. To kind of expand on that, the like very special case is this word, this phrase at rest. It means 2 things. It means the net force in the x direction is 0, and the net force in the y direction is 0. So the net force in every direction is 0 if something's at rest. If it's moving with constant velocity, it means that at the very least the acceleration. No, sorry. It also means. Sorry, let me go back there. This means net force in all directions is 0, and constant velocity means the same things. So if it is at rest or moving with constant velocity, then the net force is 0 in all directions. If it's accelerating in one dimension, then the other dimension has a net force of 0. And that's the example that I wanted to bring to you for the end of this video. So we had done a free body diagram in class of mowing the lawn, and we're going to say that in this particular free body diagram, the person mowing the lawn is pushing the lawnmower to get it moving, meaning it was at rest and they are in the process of pushing it up to a constant velocity. So it is accelerating. And the thing you need to know is just about mowing the lawn. You're pushing a lawnmower along the ground, and you are accelerating it in the direction parallel to the ground. So I just wanted to show you how you could apply this understanding of net force to our understanding of free body diagrams. And so you can write two net force expressions. So there's the net force in the x direction. And I have to think about this diagram. I have like an up force, a down force, a left force, and then a down and to the right force. So in the x direction, I know that like the friction force is going to be the negative direction force because it's pointed to the left, and that the applied force here, F, is going to contribute to the positive force. But it's at an angle. So it's not just F that is the positive x force, because it's not pointed horizontally. I have to think about, like, this force F has a horizontal component to it, and it also has a vertical component. And these are just arrows in space. It doesn't actually matter where they are, but it has two components. This component that I drew here in red is going to be related to the cosine of this angle. So the way that I would write this expression, the net force in the x direction is going to be F cosine theta. So it is the horizontal portion of this force minus the friction force. And that's the net force. And then according to Newton's third law, because it is accelerating in some direction, that is equal to mass times acceleration. So I have this expression is very mathematically useful to me because it represents the net force along the direction that the object is accelerating. So that's really important. The other thing I can write is the y direction net force. This one's a lot easier because it's in line with some of the examples we've had. So normal force and gravitational force. The normal force is the positive force, and the gravitational force is the negative force. And if you think about a lawnmower, the lawnmower is not moving up or down, and it is at a constant vertical location. And so that means if an object's position isn't changing, not only does it have a vertical velocity of 0, it has a vertical acceleration of 0. And so our second law expression ends differently, right? Instead of ending in mass times acceleration, it ends in 0. And so we get this relationship. And I just realized I did this totally wrong, and I'm going to edit this video if I can. So we're going to erase a bunch of things, and I can pause. Okay, I messed up this video. I will try and tell you where to skip to. But the net force in the y direction is really complicated because of this force F. So if I think about the vertical forces, the easy part is the normal force. The normal force is the positive force in the y direction because it's pointed up. Another easy one is Fg, and that is a negative force because it's pointed down. But there's another negative force, and so I can add another negative force to this expression. It is the vertical component of force F, and so that's going to be F sine theta. So there are three forces in the vertical direction, these two and then this component right here. Now, if you think about the lawnmower, its vertical position isn't changing. And because its vertical position isn't changing, it has a vertical acceleration of 0, and therefore its net force in the vertical direction is 0. So I have two expressions because the force F is pointed at an angle, its symbol appears in both the x and y direction, but the magnitude gets modified by either cosine or sine. And so I'm giving you some questions to work on. A couple of them have to do with this sort of thing, so this is necessary to answer the questions. Good luck.